Optimizing Graphene Polymer Composite Synthesis for Flexible Electronics, in an article available as a preproof in the journal Carbon. Researchers review the development, underlying mechanisms, and applications of flexible polymer nanocomposite fabricated through laser integration of graphene. Importance of conductive polymer nanocomposites. Conductive polymer nanocomposites are a new type of material that can be used in lighter adaptable detectors, mobile healthcare devices, battery packs, and Internet of Things adaptable networks. The composite's crystalline structure, structural durability, and electrical characteristics are modulated by the synergy impact of elastic polymeric framework and 2D conducting nanostructured additives, providing a replacement to traditional permeable dyes. Adjustable electrical devices and multipurpose detectors. Polymer integrated matrix material has a number of appealing characteristics, such as being lighter in weight, financially viable, and possessing anti-corrosive properties. High thermal conductivity composite materials have also created new opportunities in a spectrum of applications, such as photovoltaic modules, semiconductors, and biotechnological instruments. Advantages of graphene polymer nanocomposites. When graphene is mixed with polymers, it produces nanoscale hybrids with effective gas conductivity, temperature responsiveness, tensile toughness, high conductivity, and other properties, making it a preferred substance for application in culinary and electronics industries. Safe conveyance of gaseous substances and purification systems have also been highlighted as prospective industry verticals for the polymer. Graphene nanocomposite membrane. Production techniques of graphene polymer mixtures. Development of covalent graphs by in situ synthesis or melt mixing are two common methods for obtaining bulk graphene polymer mixes with uniform particles dispersion. These methods necessitate changing the entire grid capacity and further engineering to meet the requirements of flexible electronics. Instead, for electrical purposes, the region-specific modulation of the exterior layer seems to be more within budget. For this purpose, laser treatment offers a fantastic way of treating only the top layer of a polymeric layer that has previously been processed. Furthermore, this optical modification process is mask-free, ecologically sound, quick, adaptable, and enables the production of unlimited designs with variable geographic precision. Steps of laser processing. Large surface carbonization with the production of laser-induced graphite is the initial method for laser treating polymers. The refractive, electric, and hydrophilic characteristics of LIG might be tuned by modifying laser frequencies. Translucent materials, on the other hand, do not react with the majority of laser frequencies. To counter this, light reception is boosted by including molecules or nanoparticulate additions. Laser techniques are the next method for transferring graphene to different surfaces, such as laser-induced forward transfer, which uses dry or fluid substances as contributors to achieve LIG single-step voxel deposition. Ball lift has many prospective uses for composite creation. Contributor and recipient polymers are needed, which limits its applicability. Research findings. Throughout the manufacturing procedure, critical phases included the optical treatment of graphene when designed and synthesized with diazonium salts and altering the foundation to polyethylene terephthalate. Optical synthesis of Mod-G placed on a PET surface resulted in a strong, responsive, and adaptable graphene polymer nanocomposite. The significant morphological transformation generated by optical irradiation of Mod-G film was discovered to facilitate local PET melting. Pictures from scanning electron microscopy cross-sections and optical microscopy corroborated this finding. After optical treatment, data from energy dispersive X-ray spectroscopy revealed a drop in carbon percentage and an elevation in oxygen. The original carbon concentration was 81.0% with a small change following irradiation and an increase in oxygen from 15.9% to 18.5%. According to EDX, laser therapy caused major alterations in the cellular architecture and chemical bonding. Even though the relative element concentration did not alter considerably, the interior of the surface was distinguished by porosity, as opposed to the smoother nanocomposite's exterior layer. Thermogravimetric differential thermal analysis was coupled with MS of Mod-G powder to evaluate the photothermal laser processing approach to traditional thermal annealing. CO2 and H2O emissions were recorded at 150 degrees Celsius because of COOH breakdown, with persistent mass loss up to 1,200 degrees Celsius. Within the existence of optical absorbing regions, The rapid heating rate in the vicinity of the optical beam size enabled heat exchange that produced localized melting of the polymer. Furthermore, TGADTA investigation in the air revealed that the reduction in conductivity at the maximum laser flux is caused by intense heat, which causes mod G disintegration. Lastly, the researchers successfully designed mod G PET for recyclable and durable flexors, electrical heating actuators, heat, and epidermal resistive detectors. In brief, the scientists were able to effectively treat graphene nanocomposites, paving the way for cost-efficient and simple manufacturing.